Moments. Okay, what you see here, the seesaw, is actually a principle of moment. Okay, this wooden plank is pivoted about this balance. So there are two boys here, okay, where there are CG somewhere in the middle, exert a force downward. Similarly, this boy here also exert a force downward. Let's call it this W1. So the moments due to these two boys will be a clockwise moment, and that due to the other boy, W1, will be an anti-clockwise moment. This is a very old Honda advertisement where you can see the donkey is flying out in the air. The reason being the moments of the load is much heavier or larger than the moments due to the donkey. Okay, the pivot is here, so the weight of the load exert a moment that is much larger than the moment exerted by the weight of the donkey. So you see that this is an unbalanced moment. How do we define moment? A moment is a turning effect of a force about a pivot. The moment is the product of the force and the perpendicular distance between the line of action of force and the pivot. So in equation, we use capital M to represent moment, force F times the perpendicular distance. When you write this distance, you have to write this symbol here, which represents perpendicular. The SI unit for moment is Newton meter. Force have the unit Newton, distance have the unit meter, so the units for moment will be Newton meter. If I have a bin, okay, where there is a pivot right in the middle of the bin, there is a force F exerted on one end of the bin. To calculate the moment, I will have to take this force times the perpendicular distance. So that will give us the moment of the bin due to the force F. There are two types of moment, namely clockwise and anti-clockwise moment. So moment is a vector because it has direction. So let's take a look at this example whereby there is a force exerting upward on the bin. So this will provide a, okay, this is where the pivot is. You always turn towards the pivot. So this will provide an anti-clockwise moment. Then the same bin, you exert a force downward about the same pivot. This will give you a clockwise moment. So if you are talking about moments in both directions on the same bin are not equal, then there will be a resultant moment. We will look at an example later. Okay, now let's take a look at the bin whereby there are three forces acting on it, F1, F2 and F3. Moment is a vector, so we need to take sign convention. So you can start by taking clockwise to be positive. Then the resultant moment about the pivot will be given by, okay, let's start with F1. So this force F1 will cause the bin to turn this way. That is in the anti-clockwise direction. So the moment will be minus F1 times D1, where D1 is the perpendicular distance. F2 will cause the bin to turn this way. This is a clockwise moment, so it will be positive F2 times D2. F3, which is here, will cause the bin to turn clockwise also, so it will also be positive. Similarly, you can take anti-clockwise to be positive. Then your resultant moment will be just negative of what you have obtained above. Unbalanced moments. When the resultant moment is not zero, we have unbalanced moments and the body will rotate. Let's take a look at example 6.1. If I were to take moment about A, then the moment due to this force of 10 Newton will be equals to 10 times the perpendicular distance, which is 0.5 Newton meter. If I were to take moment about B, that means I put the pivot here, then the moment will be the force 10 Newton times the perpendicular distance, which is 13 cm, so it's 0.13 meters. If I take moment about C, then the moments will be equals to 10 times 0.25 Newton meter. Okay, notice that this force, right, give a moment that is always in the same direction, that is anti-clockwise. Okay, so these 3 moments that you have calculated are all anti-clockwise. Let's take a look at example 3.2. Okay, here instead of just one force 10 Newton, I add in another force F1, which is 7 Newton. So now we are going to take clockwise to be positive. Similarly, I have 3 points where I can take pivot. Let's start from point A. So the 7 Newton, okay, this one will cause the beam to turn this way. So this will be a clockwise moment. So positive 7 times the distance from here to the pivot. This will be 25 cm, so 0.25 meters. Then for the F2, it will cause the beam to turn this way, to rotate that way, so that will be a anti-clockwise moment. So you add a negative sign. So the resultant moment about A will be 1.25 Newton. Okay, now we shift the pivot to B. So taking moment about B, same thing, F1 will be positive clockwise moment, F2 will be negative anti-clockwise moment, so that will give you minus 0.11 Newton meter. Taking moment about C, we have clockwise moment F1 minus the anti-clockwise moment F2, so that will give me minus 2.15 Newton meter. So this beam is not balanced because the resultant moment about A or B or C is not 0. Example 6.3. Okay, now we are going to consider the weight of the beam. So I have force F1, F2 as well as the weight of the beam, which I call W. I'm going to take moment about the point C. So F1 will cause the beam to rotate this way. This will be clockwise moment. F2 will be anti-clockwise moment. And your W will always turn towards the pivot. So W will be clockwise moment. So I have 2 clockwise moment and 1 anti-clockwise moment. So the resultant moment will be 1.77 Newton meter. So again, the beam is not balanced since the resultant moment is not 0.